guys. So what we're going to do today is we're going to move past Algebra 1, but use some of those same concepts that we did just reviewed to look at systems that have 3 variables. So one thing you'll notice is that with 3 variables, we have to have 3 equations. Otherwise, we're not going to be able to solve it. But what it looks like when we start talking about 3 variables is instead of just looking at lines, we're going to be looking at the intersection of planes. So up here, there's just a few examples of what this could look like. So again, when you're talking about planes, you can think about, kind of more of your 3-dimensional type figure. So this first one's a good example where you have 3 different planes intersecting, and they intersect in one spot. That one place they intersect, that is your one solution. But we're not always going to have one nice solution. Just like we did with 2 variable systems, you could have infinite solutions. But infinite solutions can actually look very different. Now keep in mind, whenever we talk about infinite solutions for lines, they were the same line. Now if you have all 3 planes that are the exact same planes, yes, that is infinite solutions. But that's not the only case. So look at this second picture. All 3 of these planes intersect on this line. So every single point on that line is a solution. And we know that there are infinite points in a line. So this is actually an example of infinite solutions. All right, look at the next one. That's a pretty good example of no solutions because those graphs don't intersect anywhere. And let me backtrack real quick. Let me go back to this infinite solutions. One thing I want to make sure we understand, infinite solutions is not all real numbers, okay? We can't just say anything is a solution. What it really means is that there are an infinite number of solutions. It doesn't mean everything is. So again, think back to 2 variable systems. Let's say you had these 2 lines, they're the exact same line. There's an infinite number of points in that line, but every point is not on that line, okay? 2, -2 is not on that line, so 2, -2 is not a solution. It's not every solution. There's just an infinite number of solutions on that line. All right, now let's look at this last picture. Now this last picture is, again, what kind of makes these 3 variable systems a little unique. Just because the planes aren't parallel, there's still no solution here. Because there's not one place where all 3 of those planes intersect. So this is still a case of no solution. So they don't have to be parallel like they did for lines. They just don't have one common point of intersection of all 3 planes. All right, so what we're going to do to start, again, we're going to look at all the different methods, just like we did back with, well, we're not going to graph really because it's kind of hard to graph planes, but we'll look at a new method using matrices. We're going to start with substitution. Now, a system like this first one is a really good time to use substitution because it's a really simple system to solve by using substitution. The reason it's simple, we already know what one of the variables is. I know that z is equal to 3. So if I know that z is equal to 3, well then I can solve this second equation pretty easily. So I can do 2y minus 3 equals 5, 2y equals 8, and y equals 4. Well, now that I know that y equals 4 and z equals 3, it's pretty easy to solve this first equation because now I can plug in 4 and 3, and I get that 3x, so minus 8 plus 12 is 7, so 3x equals 3, and x equals 1. So what we're going to look at now is a system that's a little bit harder to use substitution for because now we have all 3 variables and all 3 equations. Now actually when you have a system that's set up like this, I actually prefer to use elimination. I think it's a little bit easier, you're a little bit less likely to make some mistakes, but I still want you guys to see the process of elimination or substitution and what it looks like. So what you're going to do is you're going to pick any variable in any of those 3 equations, and you're going to solve for that variable in one of your equations. So I'm going to go ahead and pick the second equation, and I'm going to solve for z in the second equation. Again, you can pick any variable that you want, doesn't matter. I'm going to use z in the second equation. So z equals negative 4x minus y plus 2. Once you've solved for one variable in one equation, you're going to take that and you're going to plug it in to both of the other 2 equations. So I'm going to plug it into the top equation. So 4x plus y minus what z now is. Now I'm going to go ahead and simplify this. So that's going to end up with 8x plus 2y equals 4. All right, we're also going to plug it into the bottom equation. So that's going to give me 12x plus 3y minus 3 times negative 4x minus y plus 2. And then we'll go ahead and simplify. So this becomes 12x plus 3y plus 12x plus 3y minus 6 equals 6. So I get 24x plus 6y equals 12. So at this point, what you would do with those two new equations is you would then have a new system to solve. So that new system is going to have those two simplified equations. So I would then solve for the intersection of these two systems to figure out what x and y are. Well, this one's a little bit unique because let's say I want to use, now again, at this point, if you want to use elimination, go ahead. Okay, once you have your new two variable system, you can choose whatever method you want to use. So if I want to use elimination now, that's fine. If I want to continue to use substitution, that's also fine. But you'll probably notice if I were to use elimination, I'm going to end up adding those equations and getting 0 equals 0. So this is actually a case of infinite solutions. But I want you guys to, again, see that process of how you can actually do substitution when you have all three variables and all three equations. But again, just keep in mind, if you end up with a completely true statement, just like we did with two variables, you're going to end up, that's a case of infinite solutions. So 0 equals 0, 7 equals 7, some always true statement. All right, so now we're going to go ahead and go to elimination. Like I said, I prefer elimination for these types of problems. I think it's just a little bit easier. So what you're going to do for elimination is you are going to pick two equations. Doesn't matter which two, and you are going to solve to eliminate one of those variables. So what I'm going to go ahead and do that I think will be easiest is I'm going to solve for z in the first two equations. So I'm going to solve for, or eliminate z in equations 1 and 2. So in order to do that, I'm going to keep the first equation the same, and then I'm going to multiply the bottom equation by 2. Then I can add these together, and I end up with a new equation. So once we've done that, we need to do the same thing for two other equations, but the same variable. So we have to eliminate the same variable. So I need to eliminate z, so I can either use equations 1 and 2, or if I want, I can use equations 2 and 3. 2 and 3 is going to be a little bit easier, so I'm going to go ahead and use 2 and 3. So I'm going to multiply the top equation, the second equation, by negative 3. So that would be negative 6x minus 9y plus 3z equals negative 12. I didn't need to change the bottom equation. And this was equation 2 and 3. And I like to write it out just because it helps keep my work a little bit more in line, makes it a little bit easier. So add those together, I get negative x minus 4y equals negative 13. So now what we're going to do, very similar to what we just did with the substitution. We're going to take those two equations and write a new system. So my new system, 7x plus 10y equals 19, and negative x minus 4y equals negative 13. Then we're just going to solve this system using whatever method you want. At this point, if you want to go back to substitution, go ahead. If you want to use elimination, go ahead. I'm just going to use elimination. I just prefer it. But again, if you want to use substitution, that will also work at this point. So I'm going to multiply the bottom equation by 7. And then 7 times 13 is going to be a negative 91. Add them together. I get negative 18y is negative 72. I end up with y equals 4. Once you know what one of those variables is, you can go ahead and plug it in. Now I'm going to plug it in to one of those equations because that's going to be much easier because, again, I only have two variables there. So I'll go ahead and plug it into the bottom equation. So negative 13, so I get that negative x is equal to 3. So x is equal to negative 3. Once you know both x and y, you can take those and plug them back into any of your original equations. So I'm going to go ahead and plug it into, let's just go ahead and use the top equation. So that's going to be 3x, which is now negative 3, plus 4y, which is now 4, plus 2z equals 11. We'll go ahead and solve. So that's negative 9 plus 16. So that's going to be 7. So 2z is equal to 4, and z is equal to 2. Now, when you write your solutions, just like we did for two variable systems, you can just say x equals y equals, or you can write them as an ordered pair. You can also write these as an ordered triple. So you could also write your solution as negative 3, 4, and 2 like this. And there's either way. So you can say x equals y equals, or you could write it out. Again, they're called ordered triples because it's not a pair now. We've got 3. All right, so if you feel comfortable, pause the video, try this next one on your own. You can use whichever method you prefer. All right, so I'm going to go ahead and use elimination again. Like I said, it's just the one I prefer. I think it's a little bit easier. I'm going to go ahead and eliminate y in the first two equations because that's basically already set up for me. So I'm going to do equation 1 and 2 for y. I can add those together, and that gives me 5x minus 13z equals 31. All right, so now I still have to use y. So again, once I've picked a variable, I need to use that variable for the next set. But which equations I pick, it's up to me. So I'm going to use the first equation and the third equation. But again, I have to eliminate y. So I'm going to multiply the bottom equation by 6. So that's going to be 12x plus 6y plus 18z. So I end up with 20x plus 20z is equal to negative 20. Now to make this a little bit easier in the solving process, 20x plus 20z equals negative 20. Everything there is divisible by 20. So I'm just going to rewrite this as x plus z equals negative 1. It's still the same equation. I just reduced it. And that's just going to make this next step a little bit easier. So now we'll solve our new system. 5x minus 13z equals 31. And x plus z equals negative 1. Again, method is up to you. Substitution, elimination doesn't matter. I'm just going to stick with elimination. I prefer it. So this becomes negative 5x. So multiply everything by negative 5. So negative 18z is equal to 36. So z is equal to negative 2. Once I know z, I can plug it back in. So x minus 2 equals negative 1. So I get x is equal to 1. Plug both of those back into any of the originals. So we'll go ahead and use just the very first equation. 8 times 1 minus 6y plus 2 times negative 2 equals negative 20. So I end up with 8 minus 6y minus 4 equals negative 20. So negative 6y is going to equal negative 24, and y is equal to 4. All right, again, on the next one, you can pick the method that works best for you. I'm going to pick elimination. I'm going to go ahead and eliminate a variable in the first two. Doesn't matter which variable you pick because you'll notice something very quickly. Let's say I want to eliminate x in 1 and 2. So I would multiply everything in the top by negative 5. Well, everything there cancels out. So I'm left with 0 equals negative 7. That is a false statement. False statements mean there's no solution. So there is not a place where all three of those planes intersect. All right, so the last thing we're going to do is just going to look at some word problems. So again, word problems, very similar setup to what you guys did with all of your Algebra 1 review, but we're going to have 3 variables now. Now again, if we have 3 variables, we must have 3 equations or we cannot solve this system. So the first one, the photo album has 80 pictures, a square, a rectangle, or a circle. There are 12 times as many rectangles as circles, 10 more squares than circles. So we're trying to figure out how many of each type of picture we have. So we've got 3. We've got squares, rectangles, and circles. So again, the first thing I'm going to do is define my variables. Really important step. So x for me is going to stand for the number of squares. Y is going to be the number of circles. And z is going to be the number of rectangles. Let me go in order. And z is going to be the number of circles. So now let's go ahead and write our equations. We know there's 80 total pictures. That means that x plus y plus z has to equal 80. There are 12 times as many rectangles as circles. Now, these are the ones that tend to get missed the most often. So again, think about this. If there's 12 times as many rectangles, there's going to be more rectangles. So in order to get more rectangles, we have to take the number of circles. I'm sorry, my rectangles is y. We have to take the number of circles and multiply it by 12. Again, if you're not quite sure if you set this up right, think about a really simple number. If I have one circle, there should be 12 rectangles. Make sure that makes sense for the values that you picked out, and in this case it does. Then the last one, there are 10 more squares than circles. So in order to get squares, we have to take the number of circles and add 10. And I keep going back to the letters, that's what I originally do, but my S's tend to look like 5, so I've switched them to X and Y. All right, so now at this point we can solve this system. This is actually going to be an easier system to solve using substitution because, again, we don't have every variable for every equation. Now, if you want to use elimination, you definitely can. But again, this is one where I think substitution is just a little bit easier. So I already know what my y is. And I also know what x is. So I'm actually going to plug both of those into this first equation. So x is z plus 10. Y is 12z. And that whole thing equals 80. So that means that I have 14z equal to 70. So z is equal to 5. Once I know what z is, I can plug that into both of those equations. So y is going to equal 60, and x is going to equal z plus 10, which is 15. So that means that there are going to be 15 squares, we've got 60 rectangles, and 5 circles. All right, this last one, looking back at some geometry stuff. So we've got 3 angles of a triangle. All right, so what we know about this triangle, it tells us that angle B is equal to 5 times angle A minus C. It tells us that angle C is equal to angle A plus angle B. And the only other thing that we need, again, we have to have a third equation if there's 3 variables. We know what all 3 of those angles add up to. A plus B plus C are going to add up to 180. Again, it's up to you what you want to use. I'm going to go ahead and do substitution. So I'm going to go ahead and substitute what I know for B into this bottom equation. So I get A plus 5A minus C plus C equals 180. Well, that's going to make this a lot easier for me because now those C's cancel out. 6A is 180, so A is 30. Now that makes it really easy to plug that back in to my other equations. So let's go ahead and plug it back into the top. So B is going to equal 150 minus C. C is going to equal 30 plus B. At that point, it's just a 2-variable system. You can solve it with whatever method you want. I'm going to go ahead and use substitution again. So I know what B is, so I'll do C equals 30 plus 150 minus C. So 2C is 180. C is equal to 90. Plug that back in. And I end up with B equals 60. All All right, so that's it for three variable systems. We'll look at two more methods next class involving matrices.